Hi, I'm Scott Jacobian. In this video, we're going to look at the forward velocity solution for planar manipulators. So by the end of this video, you should be able to solve forward velocity problems for planar manipulators. So again, we're going to use the planar 3R manipulator as an example. So for the forward velocity problem, we're going to be given the joint space variables. So we're going to be given our joint rates. We're going to be given theta 1 dot, theta 2 dot, and theta 3 dot. And what we're trying to find is the velocity of our end effector. So the translational velocity, so x dot and y dot, and the angular velocity, which is alpha dot. Okay. So previously we found the forward displacement solution. All right. What was x, y, and alpha given theta 1, theta 2, and theta 3. So in order to do our forward velocity solution, we always first need to do the forward displacement. So you can go back to the previous videos and see how we solved this forward displacement. All right. Now with the forward displacement, we can easily find the forward velocity. So we know that x dot is just simply going to be dx dt. All right, so if we take the time derivative of this equation here, you're going to get minus L1 S1 theta 1 dot minus L2 S1 2 theta 1 dot plus theta 2 dot, and then you get minus L3 S123 theta 1 dot plus theta 2 dot plus theta 3 dot. And remember, we use the shorthand notation. C1 is cosine theta 1 and S1 is sine theta 1. We can do similar for y. Y dot is just going to be dy dt. In this case, we'll get L1 C1 theta 1 dot plus L2 C1 2 theta 1 dot plus theta 2 dot plus L3 C1 2 3 theta 1 dot plus theta 2 dot plus theta 3 dot. And then lastly for alpha dot, it's just going to be d alpha dt, and that's just simply theta 1 dot plus theta 2 dot plus theta 3 dot. And that is our forward velocity solution. Given our three joint rates, we can figure out the translational velocity and angular velocity of our end effector. Now, often in robotics, we like to put things into matrix form. So let's put these three equations into matrix form and see what we get. So if we were to do that, we'll get x dot, y dot, and alpha dot. It's going to equal a matrix here, and I'll just write it out quickly. All right, and what you see here are all the terms that the first column are all the terms that multiply our first joint rate, theta 1 dot. All right, so that's everything associated with joint 1. Our second column is everything associated with joint 2. And our last column of this matrix is everything associated with joint 3. All right, and then this is times our vector of joint rates, which is theta 1 dot, theta 2 dot, and theta 3 dot. So that's those three equations on the previous slide put into matrix form. This term here, all right, on the left here, that's just simply going to be our velocity of our end effector, which is our x dot our vector x in this case. This matrix here, we're going to call the Jacobian. All right, and each column of the Jacobian is one joint of the robot. And then our last part here, this is our vector of joint rates, which is q dot. So we have v is equal to our Jacobian times q dot, again where j is the Jacobian, and it maps our joint rates to our end effector velocity. All right, and if you look at the formulation for j, right, you'll see that each column is just the partial derivative of our x vector with respect to that joint value, or joint variable, I should say. All right, and so this Jacobian plays an important role in robotics, and you'll see how it's used in subsequent videos.